Introduction. The development of cancer is very complex biological phenomenon, but in general it can be separated into two phases: an initial relatively benign phase of avascular growth, which is then followed by potential life-threatening vascular growth. The first phase is usually modeled by the biomathematical community as a system of reaction diffusion equation, or alternatively as a calcular automation. Typically, this model consists of a system of differential equivalents that describe the growth rate of population of cell as a function of cell mobility, nutrients consumption, and apoptosis, and often include one or more competing colonies of both normal and cancer cell coupled to fast time scale biochemistry process. Modeling of growing tumor over time is extremely difficult because of the complex biological phenomenon underlying cancer proliferance. The significance of the integration of computational models of tumor growth with imaging is automatic segmentation of patients' image using normal subject image to create reverse mapping of functional information from atlases to patient and parameter calibration of biophysical model. The next topic: tumor growth modeling and simulation. Methodology. Cancer processing is typically formulated as a dynamical system, a set of ordinary diffusion equations or parietal differential equivalents based on principles of conservation and constitutive laws. Tumor cells are not tracked individually but modeled as a consensual or volume fraction. This principle can be computed by reaction diffusion equivalence of the form delta Tc minus Kdc minus F is equal to 0 in multiply by C is equal to C0 in multiply by 0, with zero flux boundary condition on delta and initial conditions C0 at T is equal to 0 D. OD is a diffusion operator that models the migration of concentric cells into surrounding healthy tissues parameterized by the diffusion coefficient K is more or less than 0. While the single species model can phenomenological capture the overall dynamic of tumor growth, it does not capture the imaging phenotype of gliomas. Class of modeling assumes that tumor cells exist in interchangeable status based on the nutritional conditions of their environment. A popular hypothesis is growth or go, which stipulates that invading tumor cells are minimally. Models that follow this hypothesis represent tumor progression as a two-phase and initially exclusively proliferation phase followed by an invasion of tumor cells into surrounding tissues. This second phase can possibly transition back to a proliferation phenotype which encourage recurrence and growth of metastatic tumor. Avascular growth. Avascular growth phase is the common phase between both benign and malignant tumor can for be better experimental simulated using in vitro platform. In this phase, the growth rate is limited to diffusion and composition of the nutrients. Gompertz equation: dN by dt is equal to an minus bn log n is equal to minus bn log n by k. N is equal to size of tumor, K is equal to carrying capacity, A is equal to growth constant, and B is equal to decay rate.
Good morning, sir. I am Vasu Sutaria and I will be continuing from here. Avascular tumor growth by means of diffusion have been extensively conducted over the past decades, and many models have been presented. In early models, the process of diffusion of the dissolved substance through tissues as well as the consumption by metabolic processes was studied. Avascular growth. Tumor angiogenesis is the multiple-step process involving secretion of angiogenic growth factors by the tumor and inflammatory cells, invasions, migration and proliferation of endothelial cells through the five basement membranes, and growth of new formed vessels into the tumor stroma. Some vascular tumors can be associated with serious blood clotting disorders, making correct diagnosis critical. A vascular tumor may be described in terms of being highly vascularized or purely vascularized, referring to the degree of blood supply to the tumor. Here is the equation given for the concentration of tumor cells. That is delta C by delta T is equal to Fc N minus Hc plus Dc delta square C. Here C refers to the concentration of tumor cells, D refers to the constant diffusion coefficient, Hc refers to the rate of decay of TAF. HFCGN refers to the rate of intake by the cell N, which makes up new blood vessels. Tumor growth have the blood supply to grow beyond the diffusion limited state. In the model, the del operator is vector differential operator. Vascular tumor are a large and complex group of lesions, especially for the clinicians with none or little experience in this field. In the past, these lesions 6 caused a great deal of confusions because many appear analogous to the naked eye. Metastasis. Metastasis. Cancer cells break away from where they first formed, that is primary cancer, travel through the blood or lymph system and form new tumors, that is metastatic tumors, in other parts of the body. The metastatic tumor is the same type of cancer as the primary tumor. This is the equation for the metastasis, that is delta U by delta T is equal to Fu plus D delta square U. Here U is the activator concentration, V takes for inhibitor's concentration. U in the second half of the equation is the column vector for concentration. F is equal to column vector of reaction kinetics. D is equal to diagonal matrix of diffusion coefficient of U and V. Main characteristics of the malignant tumor is the fact that they metastasis. All tissues secrete growth inhibitors. Tumor also produce their OEM growth promoters. The following model represents the activator-inhibitor reacting and diffusing with the tumor. Metastatic cancer occurs when cancer cells break off from the original tumor, enter a bloodstream or lymph system and spread to the other areas of the body. Most metastatic cancers are manageable but not curable. Inverse problem for parameter calibration. The inverse problem of estimating biophysical model parameters P for given tumor growth model F with the ultimate goal of to provide a framework for patient-specific tumor growth stimulations and model predictions. A natural approach to estimate P is to formulate a PDA constraint optimization problem. This formulation balances the data fidelity with regularity assumptions as a model parameter P. In bracket, the inversion variable of our problem, we consider a squared L2 distance to measure the discrepancy between CIOBS X and the model output CXT. The operator F is the forward tumor model. The inversion variable P, that is example, the growth rate P equal to or greater than 0. And the state variable C are the unknowns of a problem. Sigma is a direct delta function to pick the time point Ti in T0 to which the data CIOBS are associated. The functional R in the equation 3 is introduced to alleviate the ill-posedness of the inverse problem of recovering P from COBS. The basic idea is to stably compute a locally unique solution to a nearby problem by imposing prior knowledge based on an adequate regularization of scheme, in our case represented by R. This formulation balances the data fidelity with regularity assumptions as a model parameter P. In bracket, the inversion variable of our problem, we consider a squared L2 distance to measure the discrepancy between CIOBS X and the model output CXT. The operator F is the forward tumor model. The inversion variable P, that is example, the growth rate P equal to or greater than 0. In the state variable C are the unknowns of a problem. Sigma is a direct delta function to pick the time point ti in t0 to which the data CIOBS are associated. The functional R in the equation 3 is introduced to alleviate the ill-posedness of the inverse problem of recovering P from COBS. The basic idea is to stably compute a locally unique solution to a nearby problem by imposing prior knowledge based on an adequate regularization of scheme, in our case represented by R.
Hello, my name is Kushal Mali. I will start from here. We assume that we are giving a time series in a typical clinical setting. We are usually give a single snapshot force. Indeed, when a patient presents with symptoms, the tumor is usually large and treatment, surgery, chemotherapy or radiation start immediately. Consequently, it is not practical to assume a time series of data. Any treatment that take a place needs to be incorporated into the models, which poses additional difficulties. This is not the case in the animal studies, which we do not consider here. We discussed strategies to resolve the issue of limit data in section 4. The standard approach for solving equation 3 is to introduce an additional unknown, the large multiplier lambda, and derive the stationary condition for the Lagrangian LCP lambda is equal to JP plus FCP lambda L square bracket. Derivative free, optimize automatic differentiation and finite difference of approximation of gradient are other option. Derivatives free strategies are easy to implement. They only require routine to evaluate f and j for trial parameter p. Probabilistic formulation. While the deterministic approach described above is adequate for identifying optimal parameter p such that model prediction must match some observed data, Cope's practical value remain limited. Indeed, solving equation 3 only provides us with point estimate p. In practice, we are interested is predicting some future quantity of interest pq. Say that probability of tumor recurrence after surgery due to uncertainties in the data Cope's inversion variable p and the mathematical model f, as well as the non-consequentity for the inverse problem. We require confidence interval for pq and not just point estimate p. Bayesian interference yield a systematic framework that rigorously follow mathematical and physical principles and enable us to address key question underlying predictive computerization modeling weaken quantity uncertainties as they propagate through all steps of our system, and we can access models validity and adequacy. While these features are applying a serious drawback in the significant increase in the computations burdens approach that consider a probabilistic framework and described elsewhere. Some are based on RD type system, other present methodologically for statistical model calibration, and in addition provides methodology and result for model selection and valuation. They key consider phrase field model reference 88 described as extension of the work of Odian and colleagues, considering a set of 8 RD type model and 5 variants for phase field model of varying complexity. The work mentioned is so far focused mostly on algorithmic development, discuss theoretical consideration instead in an extension of reference 144 to the probabilistic setting. They, like Odian and colleague, consider a phase yield model well prudence result for the Proteusters measure of general prior measure are provided. We note that several modeling and computerization challenge in the area remain open. The integration of biophysics tumor growth model with MPMRI can be considered as two-way couples problem where imaging provides the data required to drive calibration of a biophysical model through the solution of an inverse problem, and biophysical model can define prior for image analysis and introduce additional biomarkers. Imaging data for calibration include the geometry of the brain and the implied characterization of the underlying tissue by intensity in information from MRI modalities. Biophysical model provides probabilistic information about tumor infiltration in a specific tissue. To example, enable or guide common imaging workflows such as image segmentation. Biophysical model parameter can also play the role of biomarkers, for example the reaction and diffusion conflicts and parameter of the initial conditions such as focality and location. Imaging workflow, image segmentation and registration. In image segmentation, we seek a classification of medical imaging data into different sub each of which correspond to tissue with distinct pathophysiological properties. In our application, we are interested in differentiating healthy and diseased brain tissue and possibly subdividing future the healthy and non-healthy region in neurologically or high-grade gliomas. One typical differentiation, the anatomical brain region of WM, GM, CSF from the abnormalities visible of the vicinity of the primary tumor site. The pure tumoral ED and the tumor cure TU region, which can be the further differentiation into the enhancing tumor ET region and the union of the necrotic and non-enhancing part NE. Accurate segmentation of tumor subregion is relevant for diagnosis and treatment planning. However, tumor segmentation is quite challenging because the tumor regions are defined through intensity changes relative to the surrounding normal tissue as well as varying intensity distribution. This segmentation across multiple modalities that are often subtyped. Additional factors are imaging artifacts such as noise, motion, or magnetic field. In homogenetics, the manual annotation of region boundaries is time consuming and prone is to misinterpretations, human error and observed bias. To remove these biases, it is desirable to design automatical approach to data. The best results are achieved by machine learning techniques. This method can be argument and biophysical simulation. For example, one can use simulation as data argumentation strategy for training neural network. Integration of biophysical modeling with imaging. The fact that we do not have access to longitudinal data without treatment make the integration of biophysical modeling with image even more challenging. We need to calibrate a complex PDE model based on a single snapshot in time. Since the model is typically a dynamical system, it is impossible without regularization to calibrate model parameter using a single time data. Moreover, we do not have data for the initial date, that is an image of the patient brain without a tumor or any other information but about time history. A common strategy is stimulation. The progression of the tumor is a health. Do not allow for recovering growth pattern of tumor with complex in shape, nor do they provide information about progression or infiltration of tumor cell into healthy tissue. We discuss two framework development by our group that do not have this limitation. They integrate complex for biophysical simulation with image registration in attempt to aid imaging workflow and provide prediction capabilities. Thank you.
Hello, I am Khushi Yadav and today is our topic about neuro-oncology and in this topic clinically relevant studies. So there is an apartment need for advancement computation or algorithm for automated image analysis. Such analysis include automated brain tumor segments allocation coupled with biophysical growth model, it leading to an accurate quantity assessment of the distinct histology. Heterogeneous tumor subregional especially beneficial the clinic workflow in radiology and radiation oncology setting, as well as providing platform from radiomic research. Numerous examples in the literature indicate the benefit of the biophysical tumor growth modeling for robust patient-specific tumor characterization, especially by virtue of accurate population-based septal distribution atlas of GBM. Prediction of patient overall survival. Patient overall survival is the ultimate clinical outcome. Accurate prediction could affect the clinical decision making and the treatment planning. Numerous studies have been focusing on GBM prognostic, evolution, and stratification. This study support the benefit of incorporating biophysical growth model and show the generalization across the multi-institution data even when the model are compared with the prognostic value of current clinical and genomic makers, and demonstrate that can integration of model with imaging offers adaptive prognostic value even beyond tie current WHO classification. Example studies on prediction patient overall survival, distribution of the feature most predictive of overall survival across the long survival and short survival groups, and the black arrow points to large differences between the groups per feature. The diffusion time obtained via biophysical model of tumor growth is one of the most distinctive feature panel modified with permission from references, and the distinction of the radiography subtypes in relation to patient overall survival, the shortest survival of the isolated dehydrogenase 1 and mutant occurred in the irregular subtype. Treatment planning. Although more than 90% of tumor recurrence occur within ED, there is a limited research focused on its assessment, and its microenvironment ED appear to develop in response to angionomic and vascular permeability factor associated with the interflating tumor. As tumor outgrow the native blood supply, the result ischemia trigger further saturation of the angiogenic factor that promote vascular proliferation. Advanced complication analysis and incorporating biophysical tumor growth modeling have been conducted to evaluate the amount of the heat exerted tumor infiltration in the ED and thus assess the risk of recurrence. The value of this study has been retrospectively validated in independent discovery and replication cohort with a significant result. Furthermore, these assessments were recognized for the usefulness as a potential therapeutic tools and are currently in a clinical trial for targeted personalized closed solution planning. Along the same line, various other studies have attempted to shed light of the quantification of microscopic tumor innervation and cell proliferation, and also tumor growth rate in relation of diffusion while incorporating growth modeling. So, conclusion of this topic, we have reviewed exciting approaches toward the integration of computation model and image analysis for characterizing of neuroimaging data of brain tumor patient. We have described state-of-the-art technology for biophysics tumor growth modeling, as well as the inverse problem of estimating adequate parameter to fit the model output to available observation. We have discussed the integration of the biophysical model with the image analysis algorithm with a sober case clinical relevant result that demonstrate the benefit of such as an integration. Despite this encouraged result, we note that a successful integration of biophysical model with image analysis poses significant mathematical and computation challenge. First and foremost, biological systems involve complex, multifaceted, heterogeneous biological, physical, and chemical behavior or different spatial or temporal scale of observation. This makes the development of predictive model a difficult endeavor. Complex models result in a vast number of the parameters, which make them difficult to calibrate to medical imaging data, especially since the clinical data provide only scarce information. And aside from the complication issues, additional mathematical and modeling issues that make such an integration even more difficult. And lastly, thank you so much for watching our presentation.